want to continue our discussion of sets, function, countability, and so forth, proof techniques. And to do that, I'm going to share my screen so we can see the document camera. And I will also, actually, before doing that, I'll spotlight my video so you can see me until there are questions. Spotlight for everyone. Share screen. All right. Okay, we should be set up. Please let me know if you can see and hear me, and if you can see the document on the document camera with my fountain pen like this.
Yep.
Good, thank you. A lot of knobs and levers. So let's pick up where we left off. I sort of created this little reminder of what we did last time, what we want to talk about. So remember, we started with some characterization of functions. The topic for today is countability and what we call equinumerosity. So basically, if we have two sets A and B, and we have a bijection between them, we say that A and B are equinumerous. Again, from the Latin, having the same number of elements. This definition works even if we have infinite sets. So as most of you know, I have office hours following almost every lecture. And there's been a very interesting and robust discussion going on from those who stay to work some problems and ask questions. Last time, we continued our conversation to show that there's a bijection between the natural numbers and the integers, and therefore they're equinumerous, and also a bijection between the real numbers in the open interval between 0 and 1 and the real numbers in the open interval between 0 and 2, which is mysterious and intriguing, and we're going to go more into it today. So what I'm going to do today, the main topics, is to show you that countable unions of countable sets are also countable, and I want to talk about the algebraic numbers, which is really a way of answering a fairly deep question asked by a student, one of your colleagues, just a few lectures ago in class. But to continue where we were last time, we showed last time that the following are equivalent. TFAE is a way to abbreviate that in mathematics. The following statements are equivalent. A set B is countable. There exists a surjection from the natural numbers to B, and there exists an injection from B to the natural numbers. And we proved this. It's also in the notes. And I want to remind you that we have a very close correspondence in certain cases between the notion of an image of a function and the map function in scheme. So for example, if we have a function from A to B and A0 is a subset of A, we define the image of A0 under F to be what happens when you take all points in A0 and you F them, the image of A0 under F. Now, in the case where F is computable function, we have the following correspondence. If A0 is finite, this is exactly equal to map F over A0, and in the case where it's infinite, stream map F over A0. I'm going to go on with this. If you have any questions, please ask. Please keep in mind that in general, your lecturers, including me, cannot see the chat when we're sharing the screen. It's a deficiency of Zoom, and therefore we have TAs on the line to answer questions or to interrupt me at any time if you have a question, or you can interrupt me yourself with any questions. Please just unmute yourself and ask a question.
What does the TFAE stand for?
The following are equivalent. The following are equivalent. So three statements, all of which are equivalent, meaning each one is true if and only if any other one is true. So this is a new terminology. You haven't seen it before. It's just jargon, but it makes our work a little lighter to have this. Okay, so remember we proved an interesting theorem before. We actually gave two proofs that the natural numbers squared and cross n Cartesian product is countable. That will be a crucial thing that we will build on today. We need that as a lemma. So again, what I want to talk about today is I want to talk about infinite unions, even countable unions of sets. And I want to answer this question about the algebraic numbers. But let me motivate this by talking about the question asked by your colleague. And by the way, I would have liked to cover this in any case, but since it's a student question, it's particularly precious to me. Namely, what are we learning about the deep structure of numbers, and how can we understand these somewhat counterintuitive or unusual consequences that we're getting? So remember, we started out by saying that we have all of the real numbers, which we can draw as some kind of set like this, big set like this. And remember, we had a subset of these, which are the natural numbers. And we had a superset of those, which are the integers, which can have both positive and negative integers. And then we have a superset of those, which are the rational numbers like this. Now, one of the things we proved, and I think you can see why I did a careful proof of this with you, is that there exist real numbers that are not rational numbers. And one example of those would be our friend, the square root of 2. However, we also proved that the rational numbers are countable and the real numbers are uncountable. So there are many more real numbers than there are rational numbers. And we also proved that the real numbers, at least in binary representation, are in one-to-one correspondence with the set of functions from the natural numbers to the set of true and false. In other words, binary functions on the natural numbers. But what does it mean for them to be so many of them? You know, how do we make some intuition for that? So one of the things we're going to talk about today is the fact that you actually know lots of numbers that are like the square root of 2. They may be rational, they may be irrational. They're the roots of polynomials. And this set is called the algebraic numbers, and I'll define that precisely. So these are the numbers like square root of 2. They might well be irrational, but they're the root of a nice, well-defined polynomial. So what if we consider the very large set that contains the roots of all polynomials? How big is this set of algebraic numbers? It's clearly bigger than the rationals. Is it all of the real numbers, or are there real numbers that are not the roots of polynomials? And we'll get into that today to talk about it. Keep in mind that we might be able to prove the algebraic numbers characterize all real numbers, or we might be able to characterize a particular exception, namely a real number that's not an algebraic number. And finally, we might be able to just do this by a counting argument. If it turns out the algebraic numbers are merely countable, the real numbers are uncountable, so there must be many real numbers that are not algebraic. And when we say algebraic, I mean algebraic over the rationals, which means the polynomials to which I alluded. When I said the algebraic numbers are roots of polynomials, they have rational coefficients. Okay, so that's what we're going to try to do today. I'll bring this picture back as we think about it. And I want to start talking about how we can make some progress on this. But first, let's do a little more countability, building on our proof here that the square of the natural numbers is countable. Okay. So last time, we showed that the natural number squared is countable. And we did this in two ways. We did it by a dovetailing argument. We also did it by showing that there was an injection from n squared into n, which we then proved implies that there's a surjection from n back to n squared. But what about a set like this, n cubed, which is equal to n cross n cross n? Is such a set countable, even for a finite number of products like this? So in general, you might imagine it is, because you can imagine doing some kind of dovetailing here. But let's be explicit about that and do a construction. So I'll say theorem. Suppose we have two sets, A and B, which are countable. Then the Cartesian product A cross B is countable. So we can prove that by construction. If A is countable, there exists some function, which I'll call f, from the natural numbers onto A. And there exists some function, if B is countable, called g, from the natural numbers onto B. Both of these are onto. Okay. Now consider the map the map which I will construct called H. And H is a map from N cross N onto A cross B. And it's given by taking I comma j, which is a pair, and sending that to the pair f of I, g of j, like that. Now, H is onto Y. Well, let AB be a pair in A cross B. Then f of I covers A because there's an onto function f, and g of j covers B because there's an onto function g. And we're done. So what is going on here? Basically, the way to think about this is because n squared is countable, which we showed last time. This is the end of the proof, by the way. I'm just giving an explication or implication. So since the natural number squared is countable, which we proved last time, this implies there exists some onto function from the natural numbers onto n squared. So what we have here is the following situation. We have, there's an onto function from n onto n cross n, which is called E in this case. And we just showed here that there's an onto function from n cross n onto A cross B. And the map that goes from n onto A cross B, which we could call E composed with H using our compose function from the last time, is onto. So we can compose these to find a map all the way from the integers onto our new set A cross B. So this is a very nice way to show that the natural numbers cubed, for example, is countable. And kudos to Kyle, who covered this in recitation last time. I'm just going over it again. In fact, we can continue this by induction. I can say corollary. That's what core means, corollary. Let n be any natural number, and let A be countable, any set. Then A to the n, which is how we write A cross A cross A n times, is countable. And the proof is to use the proof above and to induct on n. Now, one thing that we'll need is a specific application of this theorem for the case where A is the rational numbers. So second corollary, letting A be the rational numbers, is that Q to the n is countable. In other words, you take n copies of the rationals and you product them together. If you do that, you're going to get a countable set. And we need this explicit function just a little bit later. Finally, some notation. It's sometimes cumbersome to write out these long products here. So we can also write something like this as the product. That's a capital pi for I equals 1 to n of A, just like summation. So product is like summation we had before. Now, a lot of you have asked really good questions about deep points in mathematics that are beyond the scope of the class, although I try to answer them. And I like sometimes to point you to later things you might take in mathematics. So this construction here, where we constructed H, given a Cartesian product, is actually a very general thing. And later, you'll take a course in algebra or category theory. And this is an advertisement. Not part of this class, not part of any question. And what you'll learn is what we've actually done is we've, in the same way that when we have a set A and a set B and we can form their Cartesian product, given functions like f and g, we're actually defining H to be the cross product of f and g. So in other words, cross product can apply not only to sets, but to functions in some sense. And the reason for this is that the cross product obviously operates on sets like the natural numbers, but it also operates on functions and things like n squared. Okay, so end of paid commercial advertisement. Those of you who are interested in going on in mathematics and computer science will find these structures and similar constructions of interest, and certainly they're very useful. But for now in this class, we can do it with our bare hands, so to speak, like this. So in summary, if we have two sets that are countable and we take the cross product is countable. We can repeat that a finite number of times. Any finite product of countable sets is countable. And in particular, the rational numbers, which are countable, when we take the n-fold product, that's countable. So you can think of the n-fold product, Cartesian product of the rational numbers, as being an n-dimensional vector. The elements of the vector are rational numbers. So for example, q squared would be points in the plane, q cubed would be points in 3 space, and so forth. And we'll need this fact just a little bit later. Okay. Now, in the same way that I defined a little bit of notation here for this product, a little notation for unions and intersections will be useful, especially when we talk about infinite unions and intersections. So what I've done here, I've only talked about finite products. We've only taken a to the n, where n is some finite natural number, but we can also take unions, intersections, and products, even when we have an infinite number of sets. And that will be extremely useful. So let's do that now. Just a little notation here. So it's convenient to index sets by the natural numbers, for example. So if we have a lot of unions, we could write something like A1 union A2 all the way up to AN. And we can denote that by a big union here for I equals 1 to n. It's an n there of AI. And similarly for intersections, if we have A1 intersect A2 intersect all the way up to AN, that's equal to big intersection, again, for I would say I within is better, I within 1 up to n. We'll use that a little bit today, but it will be extremely important when we talk about probability later, when we're regularly intersecting and unioning sets that correspond to events or probabilities, because that's the way that probability will end up being defined. So these are finite unions, pretty reasonable things to have, but we can also take infinite unions and intersections. And this is a little stranger. But you're no stranger in some sense to things that are infinite at this point. So hopefully it will feel fairly natural. So suppose I have an infinite sequence of sets that I want to take the union of. I can write that as big union like this for I in the natural numbers of AI. I have infinite unions. And similarly, I can have infinite intersections. AI intersect A2 intersect all the way to infinity. That's equal to the intersection for I in the natural numbers of A sub I. And we can be more general than that, but we don't actually need to for the purpose of this class. Okay. So now I'm going to do some things with infinite unions. And I want to see how big these infinite unions can be. And I'll use this notation. We'll come back to it if we need it. Again, my goal is to talk about the algebraic numbers, which will turn out to be an infinite union, and I want to know how big they are. So for this proof, recall, well, I have to be able to spell first. So this will become scratch paper. Recall that n cross n is countable. Now, my proof doesn't distinguish between whether the natural numbers start at 0 or 1. It applies to either one. But I want in what follows to have the natural number starting at 1, and I'll denote it this way. This is a somewhat non-standard notation. Usually at the beginning of a textbook or beginning of a paper, the mathematics professor or author or student will declare whether or not their version of the natural number starts at 0 or 1, be consistent throughout. Here we're just saying for the purpose of this proof, it starts at 1. So I want to consider the case that we introduced before, where I'm taking infinite unions of countable sets. So each AI will be countable, and the sequence here will be countable, which you can see by the index here that I is in the natural numbers. And this is called a countable union of countable sets. In other words, each individual set AI, which depends on I, is countable. And furthermore, you only doing it a countable amount up to the end of the natural numbers, so to speak. So we have a claim here that the countable union of countable sets is countable. So how do we prove such a thing? So I'm going to use the following notation, which I did briefly introduce before. So if I have a lowercase element, it's going to be an element of a set. Uppercase is sets. Collections of sets or sets of sets will be scripty calligraphic font. So I'll say let curly A be a countable collection of sets, each of which is countable. We'll write formulas in a minute, but English is really good for this. So there exists a map H from the natural numbers onto my collection of sets because my collection is countable. And we write that H of I is equal to A of I to be consistent with our earlier notation. Remember, we have this nice notation here where we're taking unions, countable unions. This is certainly countable union. I'm just now declaring that A is countable. So from a mathematical point of view, when I wrote this equation, it's clear that the union is countable because the index set is the natural numbers. The new information I'm adding is that each A sub I, which in this case is H of I as well, each A sub I is countable as well, which gives us additional structure. Okay, so we write H of I, the image of I under H is just the set A sub I like this. And that means we can write the set A very conveniently as just A1, A2, and so forth, an infinite collection. So that's our notation. Now, consider an arbitrary member of this collection, which I'll call AI. It's countable, and that implies there exists a map, which I'll call F of I. Notice it depends on the index I here, from the natural numbers to AI that's onto. And I need some notation for what it does. I'll say it sends the element J to F of I, of course, of J. And it will be convenient for me to just simply call this thing A, little a sub ij. So I'm just naming the element. So I'm defining the map. I said there must exist a map Fi that's onto from the natural numbers onto AI. I'm just saying it sends an element J to Fi of J. That's definitional. I'm just naming that element A sub ij, like an entry in a matrix. Speaking of matrices, let's order the elements like this. So here's A1, and I have A11, A12, A13, A14, all the way to infinity. I have A2, I have A21, A22, A23, A24, let's do one more, A3, I have A31, A32, sorry, this is little a, A33, A34, etc. and this continues to infinity. So I have a matrix or a table of all these elements, and it looks pretty clear. I should be able to find a way to count those, make them countable, but let's be explicit about it and write a map that counts them. So consider the map, which I'll call G, from the natural numbers squared onto this countable union. So now I'll express the countable union that I have here. This is the union for I in the natural numbers of these countable sets AI. So if I can show that there's an onto map from the natural number squared onto this countable union of countable sets, I'm done, because this set is countable by our previous argument. And basically you can see how that will work here, because I have the elements outlined like this. It kind of already looks like n1 cross n1, which are the natural numbers cross the natural numbers. So let's just do that. We're going to send PQ, which is a pair in n squared, to simply the element A sub PQ. And of course, we can write this out in functional notation and say that's just equal to FP of Q, because A sub ij is defined as Fi of j. And this is onto, and so we're done. Again, we have to use the fact that n1 cross n1 is countable to do this, from which everything follows. So the countable union of countable sets is countable. Now you may be thinking, okay, he's pretty good at bookkeeping, right? They're all keeping track of all these indices, writing these tables, getting all the details right. I mean, he'd be a really good accountant. Actually, I'd be a dreadful accountant for other reasons, but I want to say this isn't mere bookkeeping, and let me try to motivate why that's true. So this fact is actually surprising to mathematicians, because this situation doesn't always hold for other constructions. So we've just showed that the countable union of countable sets is countable, but it turns out the countable product of countable sets need not be countable. So we've looked at a creature that looked like this. I'm just recopying this business here. The countable union I in n of countable sets AI. Let's compare that to the product, countable product for I in the natural numbers of A1 cross A2 cross all the way up to AI cross all the way up to infinity, right? Sorry. So I've written the product in this notation. I've expanded it like this. Let me write it again to make sure that there's no confusion, because my writing is a little small here. We're comparing the countable union here to the countable product, the product for I in the natural numbers of AI. This thing, just expanding out what that is, that's A1 cross A2 cross all the way up to some amount AI cross all the way up to infinity.
I have a question.
Yes.
On the wording of the claim, why do we say the countable union of countable sets is countable instead of kind of like the union of countable sets is countable?
Because if the union isn't countable, it's not countable. So you see, if this, look at my set, it's a really great question you're asking here. So consider the set curly A here. This set has to be countable, right? If this set isn't countable, then my theorem doesn't hold. So I could have an uncountable collection of countable sets. Does that make sense? Look at the index here. If I replace this by, say, the real numbers, right, that would not be a countable set. So a counterexample to your claim. So the claim, let's phrase this as a question for the students. The question is, can we eliminate this word here, right?
Yeah.
And so I claim no. Let me give you a counterexample. Suppose we looked at a thing like this. Now, it isn't something we've talked about, but we certainly do it. Suppose I said the union for x in the real numbers of a set B of X. Now, I haven't told you what B of X is, right?
Mhm.
But it sort of doesn't really matter. So even if I let B of X be the single point X, this would in fact be isomorphic to the real numbers, which is not countable. And of course, it's even worse if this ends up being a bigger set. So it's important that in some sense the index be countable, which means that this set here is only countably large. Is that a good explanation?
Yes and no, but if we have that countable there, doesn't it mean we already know it's countable?
No, it just says the union is countable. So countable union refers to what's going on here. I could see how you would think that, I would see how you could think it would do that because of the nature of English. It doesn't parse that way mathematically because countable union is one term, right?
Mhm.
But if you want to be, let's say, more precise about this, we could rewrite this as claim. Let A be a collection of sets. Suppose A countable. Sorry, curly A, our countable collection is countable. And suppose for all AI in A, AI is countable. Then the union for I equals 1, 2, up to infinity of AI is countable. Does that make sense?
Yes.
So we have a crucial assumption here. We have a crucial part of the antecedent. So another way to think about this kind of graphically is that we're used to sets like A1 and A2, and these have little elements in them, you know, a little element like this, like AI, you know, this would be A1I, right? This would be A2J and so forth. But what we're talking about here is the structure of the set curly A, which has a countable collection of these little sets like this, and we're flattening the hierarchy, so to speak. So this is like a flattened operation.
Mhm.
Does that make sense?
Yes.
So I can see why the notation would be, you know, at first glance, possibly confusing, but it is correct because there's no other interpretation. You would never say countable union of countable sets. I mean, that just wouldn't make, you wouldn't say that mathematically. Countable is bound most closely to union. So I agree the English could be possibly viewed as ambiguous, but I think it's not mathematically. But at any rate, you're always welcome when there's things are given in English to ask what's the formula for it, what's the math, in which case I can, if I'm good, I can give it to you like this. It's a great question.
Thank you.
Sure, absolutely, great question. Okay, let's go back to this here. So countable union, here's the thing, the countable union of countable sets, as we've just discussed, this is countable. Here we have another beast. We have the countable product of countable sets. This need not be countable. Now, I'm not going to prove that in lecture. I've given you lecture notes on it, and you can look at it. But I just make this point. I want to emphasize that what we've done here is not mere bookkeeping. It's not proving an expected result. It's actually quite unexpected because a lot of things, when you have infinities involved, do not necessarily behave well. So, interesting fact, maybe you expected that the countable union of countable sets is countable. That's pretty cool. But perhaps somewhat unexpectedly, the countable product, by which I mean Cartesian product, of a bunch of countable sets need not be countable. Kind of remarkable. All right. So what I want to do now, I want to use this theorem. We're going to use two things. We're going to use this theorem and the fact that the rationals to the nth power are countable to look at the algebraic numbers. Okay. All right. So intuitively speaking, algebraic numbers are the roots of polynomials. I have to tell you where the coefficients of the polynomials are. In this lecture, the coefficients will be either integers or rationals. Let's just say rationals. So if I look at an algebraic number, it has to be the root of a polynomial in one variable that has rational coefficients. Similarly, if I have a polynomial with rational coefficients and I write down its roots, they'll be algebraic numbers. This is worthy of a definition. So let's define it. A real number is algebraic. And this is how I do definitions. I italics in LaTeX, underline here. And I have to say over the rationals, because that's where the polynomial coefficients are, if it satisfies some polynomial equation of positive degree, can have any fraction, any x to the minus ones in here, of the form x to the n plus a n minus 1, x to the n minus 1, plus all the way down to a1 x to the 1 plus a0 equals 0. With rational coefficients, all ai are rational numbers, and I'm going to exclude the case where all of the ai are 0. I'm not going to allow that. Okay. So what does this mean? Look at some examples. So what I want to do here is the following proof. I want to assume each polynomial equation has only finitely many roots. And then I'm going to show the set of all algebraic numbers is countable. So this is my plan, but I have to find a way to do it. Good question, what is the root? I'm going to do some examples because your question is excellent. By the way, polynomials are incredibly important. They're really the part of curvy math that you can compute things about. So they have a deep and intimate connection with computer science. So let's look at the polynomial x squared equals 2. A root of this polynomial is square root of 2. As
Professor
you know.
Donald?
Yes.
Would you mind clarifying what you mean by a root of a polynomial? That's a question in the chat.
Absolutely. I thought I meant to say I'm just getting to that. I'm going to do it by example, and then I'll define it. So give me just a little bit of rope, and if it's unclear, please interrupt and tell me whether or not I've answered your question, because I really want to do it. So let's look at the example x squared equals 2, which is the polynomial, of course, x squared minus 2 equals 0. A root of this equation is the square root of 2. Let's look at another one, and then I'll pause and see if I've started to answer your question. Let's look at x cubed minus 10 equals 0. A root of this is the cube root of 10. Let's look at one more. Let's look at ax squared plus bx plus c equals 0. In this case, what are the roots of this polynomial? Who can tell me?
Would one of them be the square root of c?
I don't think so.
Would it be the quadratic formula of like negative
Yeah, I would use,
plus or
I would
minus
use
the square root of 4ac minus 2a over 2a?
basically right. I think you got a sign, one thing flipped. So, but very good. Quadratic formula is the answer. So negative b plus or minus square root of b squared minus 4ac over 2a. So 2 roots. So these are called roots. They're the values of x that make the polynomial equation 0. And we can think of these graphically. In most cases, our polynomial, if graphed, looks like this. Here's our function f of x. These point here that make the polynomial 0 are called roots. And again, square root of 2 is a root of this polynomial equation. Cube root of 10, general quadratic ax squared plus bx plus c equals 0. The roots are negative b plus or minus the square root of b squared minus 4ac over 2a. You get, in many cases, 2 roots. And we can represent polynomials, of course, as I've done. It's obviously a function here. You could think of these polynomials in one variable as being a mapping from the real numbers to the real numbers. And what does it send x to? Well, we look at the equation up here like this, to the sum for I equals 0 to n of a n x to the n. So that's a representation. All right.
Does n have to be finite or can it be infinite, like a Taylor series, for example?
N has to be finite.
Okay.
We get a different set of functions if we allow Taylor series that can be infinite summations. So the thing about polynomials is everything is finite. They're particularly well behaved. So we now know what polynomials are, and you see that you probably already knew, but this is just different words for these. So look at our theorem that I claim I want to prove. I want to assume that each polynomial equation has only finite many roots. I'm going to try to justify that, but I'm not going to prove it in this lecture. If that's true, I'm going to show the set of all algebraic numbers is countable. A bit surprising, right? We showed the square root of 2 is irrational, and we showed that q was countable, and the real numbers are uncountable. So you might have thought irrational numbers like the square root of 2 and the cube root of 10 and things like this, you might have thought that that collection of roots, numbers, algebraic numbers, might be uncountable. But in fact, all such algebraic numbers, the set of them, is actually merely countable. So they're particularly well behaved, even though we don't have a rational number for them. So why should we believe? So in this class, we're going to either prove or write down everything. I don't feel that proving this statement is directly necessary in this class, but I have put the proof on the web, and I'm going to argue why it might be true, give you some ideas about it. You can prove this by induction, and there's a very nice proof of it that I've given you. One reason this should be true is if you look at these kind of curves, the intuitive argument is these curves don't cross the axis, the x-axis, an infinite number of times. They only cross a finite number of times. That's one way to think about it. Now, the other way to think about it is to realize this is a version of a more general theorem, which again is proved for you on the web and I want to use, which is called the fundamental theorem of algebra. Fundamental theorem of algebra. Again, I'm going to state it. It's proved in the notes, and then I'm going to use it for my proof about the algebraic numbers. So let P be some polynomial. We write that as a polynomial, and this one can even have real coefficients. So what is this? This is a polynomial of degree n. So what is degree? Let's go back here. Degree is the exponent of the highest x term. We call that the degree of the polynomial. What is this weird notation here? This is the set of all polynomials with real coefficients. And actually, there's structure to this set that we won't use in this class. But when you have a polynomial and another polynomial, you can add them, you can subtract them, you can multiply them. You usually can't divide them. So if we add to this set the operations plus, minus, and times to plus, difference, and multiply two polynomials, this particular set is called a ring, which is a famous element, famous object in mathematics. And rings you can't necessarily divide, but you can plus, minus, and times. So that's just notation for this set of polynomials. So from your point of view, P is just a polynomial of degree n, and it looks exactly like this kind of beast here. I'm allowing it to have real coefficients, but we can specialize to rationals. Then three things are true. One, this polynomial factors completely over the complex numbers. So P can be written as the product, the finite product for I equals 1 to n of x minus Ri, where Ri is a complex number. Second, P has n complex roots, which can be written R1 up to Rn. And three, not all those roots may be real, so P has less than equal to n real roots. So the proof of this, which is on the web for the class, it's a pretty easy proof, but you have to think about polynomials, uses induction. Nice exercise by induction, but I'd rather use it. For those of you interested in mathematics, this follows from a very important theorem proved by David Hilbert. It's called Hilbert's Nullstellensatz. Translated from German, roughly, Hilbert's zero locus theorem, or the theorem of zeros, which implies the fundamental theorem of algebra. So you can think of the rest of the lecture as there's a deep theorem from David Hilbert that implies our little theorem here. You could also think of this as, I'm not going to prove this in class, but I've given you the proof, and we might go over it in recitation, nice use of induction. It's a direct proof that doesn't use any fancy mathematics. So what this says is that I could take any polynomial, I can always write it as a product of linear terms like this, where Ri is a root that makes this vanish. So these might be complex, which is a little bit of a headache, but a subset of those, possibly a subset that's an empty set, will be real. So all polynomials are going to have only finitely many roots. And I'm going to use that theorem before. So again, proof on the web by induction, we might go over that. Follows from a deep theorem that you'll maybe take later as you study mathematics. Fundamental theorem of algebra, you're able to understand that now. The main barrier is you might not have worked with polynomials in a while, but we only need it for limited purposes. The main thing is that as you think of this, when we write down polynomials like this, we'd be very surprised if these little baby polynomials had an infinite number of roots. Quadratic expressions have 2 roots. Some of these only have 2 roots. Basically, the number of roots is going to be bounded by the n, the degree of the polynomial. And we can prove that rigorously. But I want to use it now to look at the algebraic numbers. Okay, so let's just do a little more here. So why am I doing this? So if x is in the reals, but it's not algebraic, sorry. So real numbers, but not algebraic, we say X is transcendental. So transcendental numbers aren't the roots of any polynomial. Very strange creatures. We haven't shown that there exist any such things yet. But in fact, if the numbers that we're talking about are countable, the algebraic numbers, they must exist. So our argument is going to be like this. We have the algebraic numbers here. There are a lot of them. We're going to show this is only countable. But since the reals are uncountable, there must exist all these other things here that are the transcendental numbers. And the transcendental numbers and the algebraic numbers partition the real numbers into two disjoint pieces. All these things are countable. The transcendental numbers actually will be uncountable. Very strange things. All right, so let's go back to what we have before and think about representation of polynomials. We know they have a finite number of roots at this point, which is fine. So if I have a polynomial like this, x to the n plus a n minus 1, xn minus 1 plus all the way down to a1 x to the 1 plus a0 equals 0, it's a cumbersome beast to think about. So consider the tuple, and I'll use physics notation, a underscore, which is just the coefficients, a0, a1, all the way up to an. And of course, this is a point in the rational numbers to the nth power. This is a lot like your exercise with streams where we kind of ignored the variable x. We can completely specify a polynomial by talking about what its coefficients are and the fact that it's a polynomial in x. So what this means is there is actually a bijection between these two things. For every polynomial, I can write down a tuple like this, which is just a list of its coefficients in vector form. Similarly, given a list of coefficients in vector form, I can write down a polynomial. So these are in one-to-one correspondence. And using our notation from before, what this shows is that there exists a mapping from the ring of polynomials in one variable onto Qn. Remember, this is just the set of polynomials with rational coefficients in one variable. So given any tuple like this, I get a polynomial. Given any polynomial, I can write down a tuple. Now, one other technical point that we'll have to think about here, in order to really specify the tuple A, I need not only to write down what's in it, but also just keep in mind that it has length n. So for example, if I wanted to hint, do something like induction on such things, I would have to count not only the length of the tuple, but the dimension n. The dimension n corresponds to the degree of the polynomial x to the n. So to denote A, we have to know not only the length of A, but the elements within it. All right. So again, remember our ultimate goal here, which is to show that our picture of the real numbers is as bizarre as we think it is. Namely that all these nice algebraic numbers over here, like the square root of 2, this is merely countable. Whereas the transcendental numbers here are what makes R uncountable. So now we're finally ready to do this. We're ready to count the size of the algebraic numbers. So let's do it. I'll say theorem. The set, which I'll call A, of all algebraic numbers over Q, meaning that polynomials have rational coefficients, is countable. So I'm going to use my theorems from before about countable unions. Countable union of countable sets is countable. And I'm going to use the fact that Q to the n is countable, which we proved before. So proof. So again, given any tuple A underscore like this, which is a vector in Qn, I can write down a polynomial. Let me write that down. So given a tuple A, which of course is equal to A0, A1, up to AN, and keep in mind that's a vector with rational coefficients in n dimensions, I want to then take that tuple and define a polynomial like this. And then I want to find its roots. So I'm going to let R sub A, remember the tuple A like this, equal the set of roots of the polynomial equation. I'll copy it again, x to the n plus a n minus 1, x to the n minus 1, plus all the way down to plus a1, x to the 1, plus a0 equals 0. So all I've done is I've said, given a tuple, which is a vector of rational numbers of dimension n, I define a polynomial equation like this, just our usual way. That has a set of roots. I let R sub A be the set of roots of that polynomial. Then my set of all algebraic numbers is equal to the following thing. Well, somehow I'm going to kind of union up these roots. So what I have to do is I have to take unions not only over the roots and the coefficients, but over the dimension. So here I have the dimension, n is a natural number. And here I have a union for all tuples A in q to the n. So notice this n depends on that n. So here I'm going to be taking unions over vectors of size n containing any possible rational coefficients. Here I'm varying the n from, say, 0 all the way up to infinity. And here I just have my set R sub A. So I take my roots and I union them up. So look what I need to do here. Given a dimension n, I then take the union over all possible vectors of rational numbers of length n. Each of those defines a polynomial like this. I take its roots, R sub A, I union those up, and I do that for all different dimensions. So the key point here is that every R sub A is finite because every polynomial has a finite number of roots. This is a countable union, this is a countable union. So this is a countable union of countable unions of finite sets, which is therefore countable. So this is countable union of countable union of finite sets, which by our earlier theorem, this is countable. Done with that proof. So the set of all algebraic numbers is merely countable. Now, a couple of things to note here. The first is that the reason this is finite is either by Hilbert's Nullstellensatz or by the fundamental theorem of algebra, which you can prove by induction. But even if it were not, even if it were the case that somehow bizarrely that a polynomial could have a countably infinite number of roots, our theorem would still hold. Because in that case, we'd have a countable union of a countable union of a countable number of roots. So this theorem is very robust to our setup and assumptions. However, we know from mathematics that actually it's finite, which is kind of great. So in short, our picture has become very interesting to try to get a feeling for what these numbers are like. We know there are all these algebraic numbers, like the square root of 2 and the third root of 10. These are all algebraic numbers. And these things here, all these things here are merely countable. However, there exist all these strange transcendental numbers. And these are not the roots of any polynomial equation with rational coefficients. Now, what are those strange transcendental numbers? What are they like? Well, you know one of them, pi, and you know another one called e. You might know some others from the gamma function. But the strangest thing is that while you would have no trouble, if I said you're going to get an A on the exam, you could spend an hour just enumerating algebraic numbers, you just write down polynomials and their roots. It's rather difficult for people to enumerate a lot of transcendental numbers. So there are a lot of these numbers, but most people don't know a lot of their names. So this is very strange. These are uncountable, or UC, because the real numbers are uncountable. So lots of these strange creatures that are not the roots of any polynomials that have rational coefficients. So I want to sort of say this is a really interesting situation we have, and to give you a little bit of mathematical culture to think about this, this point. So one thing is this is a positive result. Because the algebraic numbers are countable, and because polynomials and their roots are really the fundamental basis of most geometry and algebra all the way through college. In fact, we could, in an automated fashion, prove most of the geometry theorems that you had in high school for your geometry class. Because they're really countable, we can use things like streams to represent algebraic numbers. And we can do computations on algebraic numbers, which include lots of curved things and straight things. It's remarkably powerful. So the fact that in some sense, algebraic numbers are countable means that computations with polynomials are tractable to an extent computationally. And this is the basis for a lot of math and science, a lot of CAD/CAM, a lot of engineering, a lot of finance, because we can actually get at these things and we can deal with them because we have techniques like streams, techniques like induction, in order to prove things about them and iterate over them. So actually, we're quite happy that the algebraic numbers, while huge and very expressive, are countable. It still is puzzling and weird and a very deep thing that there are transcendental numbers that are not the root of any polynomial equation with rational coefficients. But moreover, it's strange that there's so many of them and we don't know the names. Most people don't know the names for a lot of these creatures. So I want to sort of close. By the way, when I say close, what I mean is I'll stay around for office hours and take any questions that you might have. But what I wanted to do is I wanted to say that the topic of these strange transcendental and algebraic numbers is a thing of almost cult fascination among computer scientists and mathematicians. So for example, you might know the story of Évariste Galois, whose work is closely related to the work we're talking about. He was born around 1811. He invented Galois theory, the fundamental for a lot of algebra and geometry, which is one of the ways you can get at these problems. And he died in a duel after laying out the ideas the night before at age 21, which is, after all, the age at which many mathematicians do their best work. And just to sort of, lighten the mood a little bit, I want to say that he is sort of a revered figure in computer science and mathematics. Many people view him as almost cult figure-like status. And I wanted to say that we can have a little fun with this. I want to share my screen and tell you a little story, a little musical interlude. So when I was living in New York and later in California, I actually played in two bands of some interest to nerds like me. One was Severe Tire Damage, which was the first band ever to play on the internet. And the second was Harmful if Swallowed, unnotable except that we were all computer scientists and wrote songs about mathematicians, including Évariste Galois, who you certainly would want to look up. And I want to close the lecture by playing you a little song about Évariste, who wrote down the basis of Galois theory the night before a duel, founding the field in many ways. We'll share the computer sound for you and let you hear this to understand at least how I feel about Galois. The great mathematician Dexter Cozen wrote this song and was singing. This was recorded in the 90s. So we'll do this, then I will come back and take questions and stay around for office hours. So enjoy. So,
dry hand aching, red sky dawn breaking, candle low, fever high. Today I'm gonna die. Every sky. song in my ear that no one else could hear. Got it down, but there's no time. No time to make it rhyme. Every step. Every step. Blood pound, adrenaline run. And turn around, face to the sun. Raise arm, point gun. So much left undone.
Okay, that concludes our musical interlude. Again, Galois theory isn't necessarily the best way to understand transcendental numbers, but it is a way to have access to some of these questions. With that, I will be happy to take questions for a few minutes, and then I will, if you have any, and I'll stay around afterwards if anyone would like to talk after class as well. Any questions?